Hello, welcome to Cardio Flash College, a place to learn cardiology with flash animations. Today we have a very special video because it is made in collaboration with another YouTube channel. Thus, it is an honor for us to present José Luis Oltra, physicist and scientific communicator, member of the CNEO community, and creator of the YouTube channel 42 and the YouTube Shorts channel 43. And together we are going to explain everything you have never been able to understand about the physical principles that govern the functioning of cardiac magnetic resonance imaging.
Hi Renier, thank you so much for the invitation. I hope to help everyone to understand at least a bit of the concepts that we're going to talk about today. Besides, we will see how the most basic physics can be applied to an important field in our day as it is the health. Are you ready? Let's begin!
As you know, cardiac magnetic resonance imaging, also known as cardiovascular magnetic resonance or CMR, is a non-invasive imaging technique that allows us to accurately study the structure and function of the heart, as well as other cardiovascular structures. This allows us to characterize tissues, measure anatomical structures, quantify flows, analyze the contractile function of the ventricles, and evaluate myocardial perfusion, among other things. And all this without using ionizing radiation or iodinated contrast media. However, we all know that, as precise as cardiac MRI can be, it is very difficult to interpret the images obtained if we do not understand how the acquisition process works. Thus, it is helpful to be familiar with some basic concepts, such as the electromagnetic field, the nuclear spin, the magnetization vectors, the longitudinal and transverse relaxation time, among others. And this is where the crux of the matter lies, because many of these concepts belong to the field of study of traditional physics, which is why it can be a real headache for many health professionals. However, with today's video, we will definitely solve this problem, since we have the help of 42.
Effectively, so don't worry, because we're going to start from the beginning of all. First thing to remember is that matter and the objects that surround us are formed by molecules. Thus, these are made by atoms, which are made for subatomic particles, principally protons, neutrons, and electrons. Protons and neutrons occupy the inner center of the atom and conform the nucleus, while the electrons form a sort of cloud that goes around them. Well, all these particles have intrinsic and fundamental properties such as mass, charge, and spin. Mass of an atom corresponds mostly to the nucleus, because the electron's mass is 200% lower than protons and neutrons. To represent the mass of a chemical element, we use the mass number, which equals the sum of neutrons and protons that exist in the atom, and is represented by the letter A. When we talk about the charge, we can say that protons have positive electric charge, and electrons have negative, and neutrons don't have charge at all. They are neutrals. Moreover, an atom in its fundamental state tends to be electrical neutral due to having the same number of protons and electrons. We can also name the atomic number, which equals the total number of protons that an atom has, and is represented by the letter Z. This number allows us to differentiate the chemical numbers from each other. For example, a sodium atom has an atomic number of 11, which means that sodium has 11 protons. A magnesium atom has an atomic number of 12, so it has 12 protons, while a hydrogen atom has an atomic number of 1 and has 1 proton. This atomic number is very important because the quantity of protons of an atomic nucleus defines which chemical element it will be. In other words, an atomic nucleus that has 11 protons will be a sodium nucleus, no matter if it has 1, 15, or 1000 neutrons. Lastly, the spin is another intrinsic property of the particles and is related to angular momentum. Normally, spin is seen as related to the rotation of the particles, but this isn't right. It's more correct to picture it as if these particles have a favorite direction, as if pointing in a certain direction. This is a property of the fundamental particles, and, like the electric charge, it can be accumulated or contracted. Thus, compound particles like protons or atom nucleus will have a spin. The atom nucleus, having protons and neutrons, which are composed of quarks, also has a spin, a nuclear spin. Protons and neutrons within the nucleus tend to pair themselves, making spins of two different particles contract each other two at a time. resulting in the nucleus cancelling its total spin and turning it to a zero. This because it's energetically favorable. But of course, spin is counteracted by protons in one side and by neutrons in the other side. Then, nucleus that has odd numbers of protons, neutrons, or both will have nuclear spin different to zero. Protons, neutrons, electrons, and other subatomic particles are governed by what it is known as fundamental forces. This will tell how the interaction of the subatomic particles with each other will be, and they are four: the gravitational force, the electromagnetic force, the nuclear weak force, and the nuclear strong force. In this way, and as you can imagine, magnetic resonance will use the electromagnetic force to observe the internal functioning of an organ, and specifically the heart. But what is the electromagnetic force? Well, the electromagnetic force or electromagnetic interaction is what governs the movement and behavior of the particles with charge. In the same way that any object with mass is affected by the gravity, any object with electrical charge will be affected by electromagnetism. In the fundamental level, the electromagnetism is a single force, but to be practical we can split it into related but different forces: electrodynamics and magnetism. Though there is a fundamental difference with gravity, and that is that for the electromagnetism, there are two electrical charges, positive and negative. When talking about gravity, all the bodies with mass are attracted to each other. But for the electromagnetism, the bodies that have opposite electrical charges will be attracted, and those with the same electrical charge will repel each other. As we said before, protons will have positive electrical charge and electrons will have negative electrical charge, and that's why electrons stay attached to the atomic nucleus and they'll go wherever they like, because opposite charges attract each other. These particles will create electrical and magnetic fields around them, and will attract or repel other particles. Electrical fields will be created by charges at rest, in other words, charges that are still. Meanwhile, the magnetic fields will be created by the moving charges.
Very good, 42. Now we know that intrinsic properties and fundamental forces such as electromagnetism can govern the behavior of the atoms in our body. But what does all this have to do with cardiac MRI?
It's easy, Renier. The answer is in the hydrogen atoms. You see, the hydrogen is the universe's most abundant element, and so it is for the humans too. As we said before, the hydrogen has an atomic number of 1. Then it means it only has 1 protons and no neutrons. Hence, the hydrogen atomic nucleus is just a single particle, the proton, and its spin can be counteracted by other particles, so hydrogen spin is different to 0. Nuclear spin will be responsible for showing a little magnetic field around the proton. That is what we know as the magnetic momentum of the proton. During magnetic resonance, we take advantage of this tiny magnetic field and the fact that the hydrogen is present in our organism to observe the different tissues in ways that would be impossible if we use our bare eyes. Hydrogen can be found in the body as a part of the water, but also in the huge quantity of biomolecules that form us. Lipids, for example, have a lot of hydrogen within them. In the natural state of the hydrogen that forms the different molecules of our body, those magnetic momentums, formed by the hydrogen nucleus, point to a random direction. In this way, they contract each other and don't create a macroscopic magnetic field. Nevertheless, when we apply an external magnetic field, like what happens in magnetic resonance, these little fields that correspond to each hydrogen molecules tend to align with the main magnetic field, which is more intense. In an ideal case, all the hydrogen atoms of the object of study would have all their nuclear spin aligned and will point to the external magnetic fields. But that's not what happened in reality. Hydrogen atoms will indeed align to the main magnetic fields, but their spin would be parallel or antiparallel to it. Body temperature will add energy to the system and some kind of randomness in the particles' movement, making them to go far from the ideal condition. The result will be that at room temperature and with typical magnetic fields of 1.5 Tesla of intensity, there will be an excess of parallel hydrogen nuclei against antiparallel ones. Though this excess won't be too big, normally just few parts per million. Still, this excess will generate a net magnetization to the direction of the main magnetic fields. But of course, once the hydrogen nuclei are aligned with the main magnetic field, they will all stay calm, and that doesn't help us. What we need now is to slightly perturb those nuclei to see how they respond to our perturbing, and thus be able to study the corresponding tissue. We will do this by sending radiofrequency magnetic pulses. That is, basically, generating a less intense magnetic field that oscillates with megahertz frequencies. In doing so, the hydrogen nuclei will start to become misaligned with the main magnetic field and will have a precess movement. A precession movement is, for example, the one shown by a spinning top when it remains stable at a point and its axis of rotation describes circles around the vertical. The same will happen for hydrogen nuclei, which will have a pitching movement around the direction of the main magnetic field, and the frequency of this precession movement will be dependent on the intensity of the applied radiofrequency magnetic field. Well, the net magnetization vector that is generated in the tissues after being exposed to an external magnetic field will be a longitudinal magnetization vector, because the vector is parallel to the longitudinal axis of the magnetic field. But the magnetic resonance equipment will only be able to detect variations in the magnetization vector that occur in a transversal way to the magnetic field, and therefore we will need to disturb it with a radiofrequency pulse. These radiofrequency pulses will be nothing more than radio waves emit at a specific frequency. Radio waves are light, like the visible light that our eyes are capable of detecting or the ultraviolet that damages our skin. But in this case, it will be a less energetic light, and therefore it will be a non-ionizing light, or radiation, and won't be a problem if irradiated on the patient. In this way, the nuclear spins will absorb the energy of the photons that form light and will enter in resonance, because the pulses will have been prepared in such a way that the energy of those photons is just the energy that the hydrogen nucleus needs to jump from the state with a nuclear spin parallel to the magnetic field to a nuclear spin antiparallel to this field. As we have already mentioned before, by emitting the radiofrequency pulse, we will be able to modify the direction of the nuclear spin of the hydrogen atoms, making them to rotate around the parallel or antiparallel position like a top with a movement that we call precession. This deflection of the hydrogen nuclei spins will not occur suddenly, but it will occur gradually, as the pulses are applied. This will cause the angle they form with the direction of the main magnetization vector to increase. This is what is known as a nutation move, which is nothing more than the variation of the angle of precession, in such a way that the amplitude of this angle depends on the intensity and duration of the radiofrequency pulse. Therefore, the radiofrequency pulse must have the necessary intensity so that the number of spins that precess in parallel and antiparallel is the same, neither more nor less. Thus, an angle of inclination of the magnetization vector of 90 degrees, a minimum longitudinal magnetization vector, and a maximum transverse magnetization vector are achieved. At the end of the radiofrequency pulse, the nuclei that had been excited release the acquired energy by emitting photons. Therefore, the spins that had achieved an antiparallel state return to the parallel state. The equilibrium is restored, and the original longitudinal magnetization vector appears again. This process is known as nuclear relaxation and is carried out by two coexisting mechanisms. These are recovery of longitudinal magnetization and decrease of transverse magnetization. The recovery of the longitudinal magnetization, also known as longitudinal relaxation, is given by the ability of atoms and molecules to throw the energy that the excited spins release after the radiofrequency pulse has disappeared. So that means this phenomenon will be conditioned by the composition of the medium surrounding the excited spins. There will be areas and tissues of the body where this longitudinal relaxation will be easier and faster, and others where it will be slower. This relaxation rate will depend on the size of the molecules containing the excited hydrogen atoms and the rate of the movement they describe. When the molecules rotate and move, they give rise to a small transient magnetic field that can affect the surrounding molecules. When the frequency of this magnetic field is like that of the radio frequency pulses, and therefore to the resonant frequency of the nuclear spins, the release of energy will occur much faster. Thus, longitudinal magnetization recovery is defined by the time constant T1, which represents the time required to recover 63% of the original longitudinal magnetization vector. The slower the energy released during longitudinal relaxation, the longer T1 will be. Lipids will generally have a very low T1, as they are the right size and structure. Significantly larger or smaller molecules, such as water molecules, will have much longer T1 times. However, tissues with a lot of water and an important presence of macromolecules, such as metal, will have a lower T1 relaxation times. Moreover, the decrease in transverse magnetization is also known as transverse relaxation, and depends on the time it takes for the spins to lose the precession synchrony after the interruption of the radiofrequency pulse. That is, while the radio frequency pulse is active, the nuclear spins process at the same rate and in the same direction. But when cutting it, each core will take a random move which will desynchronize this move. This loss of synchrony will depend on the effect exerted by the magnetic microfields of the other hydrogen nuclei in the environment and the lack of the homogeneity of the external magnetic field to which they are subjected. Therefore, the more homogeneous the external magnetic field and the lower the spin-spin interaction is, the interaction between two atomic nucleus, the slower the desynchronization of the spins will be after finishing the radio frequency pulse. In this way, the transverse relaxation is defined by the time constants T2 and T2 asterisk, which represent the time required to lose 63% of the transverse magnetization vector. Again, the slower the spins process out of synchrony, the longer T2 and T2 asterisk will be. When the transversal relaxation depends only on the spin-spin interaction because there is no inhomogeneity of the external magnetic field or because it doesn't affect it, we will work with the time T2. When the spin-spin interaction and the inhomogeneity of the external magnetic field simultaneously participate in the transverse relaxation, then we will work with the T2 asterisk. This will mean that T2 asterisk will always be shorter than T2, since the influence of the both causes a faster loss of synchrony. All this is what happens in the body, but when it comes to detecting a signal, what we will see is a magnetic field that oscillates and gradually decays. This is what we know as free induction decay or FID. This free decay of the induction will be the electrical signals generated by the movement of the magnetization vector after the application of the radio frequency pulse that we will detect later. These signals are acquired by the spectrometer and processed by the computer during the magnetic resonance, so that, using a specialized software, images of the tissues can be obtained, which are finally represented on a grid scale. Easy peasy, right?
Well, thank you very much, 42. Now it is clear that this grayscale is built based on the times T1 and T2 that the different tissues have. Thus, cardiac MRI can characterize the tissues studied by means of two different tools. These are the repetition time and the echo time. Okay, let's start with the repetition time. This is a term used to define the time that elapses between two radio frequency pulses. Thus, with a fixed repetition time, tissues that have a T1 shorter than the repetition time will have more longitudinally relaxed spins. Therefore, there will be more spins available to resonate with the next radio frequency pulse, and the signal produced in this tissue will be hyperintense. In contrast, tissues with a T1 longer than the repetition time will have fewer longitudinally relaxed spins. Therefore, there will be fewer spins available to resonate with the next radio frequency pulse, and the signal it produces in this tissue will be hypointense. Now let's talk about echo time. Although it may be difficult to explain, we could say that while the spins process in synchronization with the radio frequency pulse, the transverse magnetization vector generates an echo that can be captured by MRI. When the radio frequency pulse ends and the spins begin to lose precession synchrony, the echo that was produced is simultaneously lost due to the loss of the transverse magnetization vector. Thus, the echo time is that which elapses from the time a radio frequency pulse ceases until it is decided to capture the echoes released by the spins in the transverse relaxation phase. Thus, with a fixed echo time, tissues with a T2 shorter than the echo time will not be able to produce any signal, since there will be no echoes available to be picked up by the MRI. On the other hand, tissues with a T2 longer than the echo time may be able to produce signals, since there would still be echoes available that can be captured by MRI. In this way, using both times, grayscale images can be obtained with acquisition sequences weighted in T1, T2, and proton density. T1 weighted sequences use a short repetition time and echo time, so that tissues with a shorter T1 will produce hyperintense images, and tissues with a long T1 will produce hypointense images, while differences in T2 will not be able to be seen contrasted, because with such a short echo time, all tissues emit echoes simultaneously and cannot be differentiated from each other. With these sequences, water and bone tissue are opaque or hypointense, but fat, healthy soft tissues, and gadolinium present a signal of variable but high intensity. And what about the air? Well, in this sequence, as in any other, the air is opaque because it does not have hydrogen atoms that resonate with the MRI. On the other hand, proton density weighted sequences use a long repetition time and a short echo time, so that tissues with a short T1 and a long T1 will be able to resonate in unison with the following radiofrequency pulse, not being able to establish differences between them. With respect to T2, the differences cannot be contrasted either because with such a short echo time, all the tissues emit echoes simultaneously and cannot be differentiated. Finally, the intensity differences produced will depend exclusively on the density of protons or hydrogen atoms that the studied tissues have. In this way, it is understandable that both water and fat are the most intense tissues in a sequence enhanced in proton density, since the structure of these molecules has a high density of hydrogen atoms. Finally, T2 weighted sequences use a long repetition time and a long echo time, so that tissues cannot be differentiated based on their T1, but rather based on their proton density and T2 time. Thus, tissues with a T2 longer than the echo time may be able to produce signals, while tissues with a shorter T2 will not. With these sequences, water is hyperintense, fat is intermediate, and bone tissue is opaque. Well, at this point in the video, we could simplify cardiac MRI in the following way. First, the patient is placed inside a large cylinder-shaped magnet. Then, a magnetic field is generated in order to align the vector of magnetization of the nuclei of the hydrogen atoms that make up the patient's tissues. Subsequently, radiofrequency pulses are applied with the aim of disturbing the magnetization vector, first exciting and then relaxing the atomic nuclei. The electric signals obtained during the nuclear relaxation process are converted into images by the team through the phenomenon known as induction freefall. Finally, different image sequences are obtained after adjusting some variables such as repetition time, echo time, intensity of the radiofrequency pulse, among others. As you can see, it has not been that difficult, because with the help of 42 and the magic of animation, we have been able to familiarize ourselves with the general physical principles that govern the functioning of the magnetic resonance imaging. However, we still have a lot to see on the subject, especially the clinical applications of this tool in the field of cardiology. So if you want more information about some clinical aspects of cardiac MRI, such as the sequences of most popular acquisitions, the contrast media used, the cardiorespiratory synchronization process, or the most common artifacts, it will be necessary to develop it in another video, since today we do not have more time. It has been all for today at Cardio Flash College. We hope you liked the video. If so, subscribe to the channel and leave a like. We'll see you in the next class. And remember, don't come late. Bye!